Hello, this is part two of the molecules that we're going to be looking at in terms of ultimately figuring out what their molecular geometries are. We looked at a number of molecules on the first part of this, and we're going to look at the remaining types in this session. In this, we've been trying to determine the number of electron domains around the central atom that we see in these simple molecules. Where an electron domain can either be a non-bonding pair of electrons, or it can be electrons that are in bonding pairs. And each of the following count as a single electron domain: a single bond, a double bond, or a triple bond. So our electron domains are non-bonding pairs, single bonds, double bonds, or triple bonds. Each one of those is just a single electron domain. So let's look at chlorine trifluoride. Chlorine is going to be our central atom. Around it, we've got two non-bonding pairs of electrons. We've got three single bonds. Each one of those counts as just an electron domain. So in all, we have 5 electron domains. We saw in the previous video that this gives us a hybridization that we refer to as being sp3d. It has electron domain geometry of being trigonal bipyramidal. And it's a type of molecule that I'm going to call AB3E2. Where A represents the central atom, B is the 3 peripheral atoms, and E2 shows that we've got 2 non-bonding pairs of electrons in the central atom. In the trigonal bipyramidal electron domain geometry, we've got 2 different types of positions around the central atom. We have these axial positions. We also have an equatorial position, in that between the axial and the equatorial there's 90 degrees, and around the equator between each of the electron domains are 120 degrees. And so in this ClF3, the way those non-bonding pairs of electrons arrange themselves are actually to be along the equatorial position. Remember, we're using the valence shell electron pair repulsion theory. That those electron pairs want to maximize the angles between them in order to minimize repulsive forces. And so in this particular arrangement, this molecule, if I turn it on its side, it's actually T-shaped. And the bond angles will be a little bit less than 90 degrees. The reason they're not ideally 90 is because those non-bonding pairs of electrons have greater repulsive force than do electron domains that are in bonds. So that's ClF3. Next one is a polyatomic ion, IF2-. Iodine is going to be my central atom. And around it, I've got 3 non-bonding pairs of electrons. We made 2 single bonds. Once again, we have 5 as our total number of electron domains. That means our hybridization is sp3d. That means we've got a trigonal bipyramidal electron domain geometry. If I label a type of this, we could say it's AB2E3, central atom A, which is the iodine, 2 peripheral atoms, B, which is the 2 fluorines. Now I've actually got 3 non-bonding pairs of electrons on the central atom. And so, once again, as we look at this molecule, where that 3rd non-bonding pair of electrons is going to go, if we go back to the diagram we looked at before, they're going to go on an equatorial position. And so this molecule is going to wind up being linear. The molecular geometry, we're only looking at the atoms. Yes, the non-bonding pairs influence what this molecular geometry is going to be, but we don't use that as part of our description. And so that bond angle is going to be 180 degrees. And this molecule winds up being nonpolar. I've been talking about that in the other ones. I forgot about this top one. It winds up being polar. We'll come back and talk about polar versus nonpolar a little bit later. But as you might be going through this video to review it for a final exam later on, I'm going ahead and do that notation now. Sulfur hexafluoride, SF6. The sulfur has no non-bonding electron domains. So it's made 6 bonds. It's got an excess of an octet around it. So it's got 6 electron domains in all. So we've got a new hybridization type. We've graduated from 5 to 6. This is going to be sp3d2. sp3d2. This is a type of molecule we call AB6. But the important thing is that it's sp3d2. And what this is going to give us is something that's called an octahedron, or it's an octahedral electron domain geometry. And that is, you could think of it as being 2 square pyramids placed base to base. And so there are actually 8 faces to this octahedron. Since there are no non-bonding pairs of electrons on that sulfur, the molecular geometry and electron domain geometry are the same, so it's also octahedral. The bond angles turn out to all be 90 degrees because the atoms are all the same. There are no non-bonding pairs on the central atom. This guy winds up being non-polar. Bromine pentafluoride, BRF5. We've got 1 non-bonding pair on the bromine. It's made 5 bonds. So once again, our total number of electron domains is 6. I said 5 bonds, but remember that single bonds or double bonds or even triple bonds, they all count as a single electron domain. So there are 5 bonding domains. If the total number of electron domains is 6, it's sp3d2. That means it's got an octahedral electron domain geometry. It's a little bit different. This guy is AB5E. Got 5 atoms around the central atom plus a non-bonding pair of electrons that's represented by the E. And so maybe you can visualize that being the base of the pyramid, the floor being above. This becomes a square pyramid, or we could refer to that molecular geometry as being square pyramidal. It's different than what we saw in sp3, where we had a single electron non-bonding pair of electrons amongst the 4, and that gave us a trigonal pyramidal molecular geometry, a 3-sided pyramid. If you're looking down on the apex, this one gives you 4-sided. If you're looking down from the apex, discounting the base. So those bond angles they're going to be squished up a little bit. The non-bonding pair has a little bit greater repulsive forces, so those ideal bond angles can be a little bit less than 90 degrees. And this guy is going to wind up, this molecule is going to wind up being polar because of that non-bonding pair of electrons and the overall shape of the molecule. You've got to consider both of that. Our last example, xenon tetrafluoride. We look at the xenon in the center, the central atom. It's got 2 non-bonding electron domains, 2 non-bonding pair of electrons, each worth 1 electron domain. It's made 4 single bonds, each worth a electron domain. So once again, we've got a total of 6 electron domains around the central atom. That means we've got a hybridization of sp3d2, and it's an octahedral electron domain geometry. The electron domain geometry describes the arrangement of electrons around the central atom. Here we could call this AB4E2. A central atom A, 4 peripheral atoms we denote by B. It's got 2 non-bonding pairs of electrons. And so, the way this really looks, there's my xenon and the 4 fluorines. And we don't really have axial and equatorial in octahedral like we did in the trigonal bipyramidal. But we got these 2 non-bonding pairs of electrons, and they want to maximize the distances between them in order to minimize the repulsive forces. So they're going to go on the, I'll call the pseudo-axial position. And so the molecular geometry only describes how the atoms are arranged. So this winds up being a square pyramid. A square, they're all in the same plane. These are square planar. And those bond angles wind up being 90 degrees. And because the atoms are all the same, and the non-bonding pairs of electrons are on opposite sides of one another, everything has something to sort of cancel it out, so to speak. If we talked about the polarity of the molecule, it would be nonpolar. We'll come back and go in much more detail about whether molecules are polar or nonpolar a little bit later. So this has been part 2 of looking at molecular geometries using the VSPER, valence shell electron pair repulsion theory. Thanks for listening and watching.